Hello and welcome to video 2 of the M2 chapter, Centres of Mass. Question on the screen here to review the first video. 3 particles of masses 5, 3 and 7 kilograms are placed at the points this, this and this respectively. Find the coordinates of the centre of mass of the 3 particles. So the formula we were using, or the idea we were looking at, was the sum of the individual masses times by, in this case, x bar, but we could also use y bar for the y coordinate, is equal to the sum of the individual moments of each particle, mi xi. So here, the sum of the masses, we've got 5g plus 3g plus 7g times x bar, the thing we want, is equal to the sum of the moments. So that's 5g times the x coordinate of that particle, minus 3, plus 3g times the x-coordinate of that particle, 2, plus 7g times the x-coordinate of that particle, which is 3. Remember, respectively means you keep the order for the lists. This one matches this one with this one, and this one with this one. Now I just go ahead and solve my equation. Here we've got 15g x bar, and over here we've got 12g. The g's cancel out. So x bar is equal to 12 over 15, which is 4 over 5. The particular wording of the question, though, it says find the coordinates. So I shouldn't really stop there. I should now state that the coordinates of G, the centre of mass, are 4 over 5, 0. In this video, we're taking this idea forward to find a centre of mass of particles arranged on a plane. And there isn't really much different here from what we did in the first video, except a slightly better way of approaching the calculation. We know to calculate the centre of mass of a system of particles on a line, we can use this for the x-coordinate or this for the y-coordinate. To find it arranged on a plane just means you have to do both, the x-coordinate and the y-coordinate. So you could do what we've been doing in 2 separate calculations, but there is a slightly better way, and that is to use vectors. So we can do both calculations in one set of working. Using the position vector r in bold to represent vector, the above results combine to be written pretty much the same thing, but with an r here, that's the position vector of the individual particles, and r bar, which is the position vector of the centre of mass. Some examples then. Find the coordinates of the centre of mass of the particles with masses 2, 3 and 5 at the coordinates this, this and this respectively. And again, I will draw the diagram here, although I wouldn't normally. Let's just quickly sketch out where these are. So 1, 2 is around about here. This is the 2g weight. 3, 1 somewhere down here. This is the 3g weight. And 4, 3 is maybe over here somewhere. And that is the 5g weight. And we're trying to find a point that's maybe around here-ish, which represents all 3 of those in 1. And we know by adding the weights this is 10g. But the question is, where is it? X bar and Y bar. For this first example, I will do both calculations separately so that on the next example you can see how much quicker it is to combine the working. For X bar, we've got 10g times x bar has to equal 2g times the x-coordinate of 2g, which is 1, plus 3g times its x-coordinate, which is 3, plus 5g times its x-coordinate, which is 4. We've got 10g x bar, 31g. So x bar is equal to 3.1. Then for the y bar, we've got 10g again, but now we're looking in the y direction. 2g times its y-coordinate, plus 3g times its y-coordinate, plus 5g times its y-coordinate. And that gives us 22g. 10g y bar, which gives y bar as 2.2. So the coordinates of the centre of mass, which unless I'm told otherwise I will always call g, is 3.1, 2.2. A very similar example here, but I'm going to use vectors instead, you'll see that the calculations are the same. It's not really reducing your work, it's just reducing how many equations you have to write. So find the coordinates of the center of mass of the particles with masses these at coordinates these respectively. We do have 4 of them this time though. I won't draw a diagram, I'm just going to launch straight into the calculation. So on the left we're going to combine the weights to get the total weight. So we've got 4g plus 2g plus 8g plus 6g, and then we need to times that by the x bar or y bar, but here I want to do both together, so I'm going to use vectors, x bar, y bar, and that has to equal the moments for each individual particle, and they've each got an x and a y coordinate, so I'm going to do this same idea for each one individually over here. So the 4 kilogram mass, which is a 4g weight, has to be multiplied by -1 for the x coordinate and 3 on its y coordinate, plus the 2g weight, the 2 kilogram mass, times -2 minus 4, plus 8g, the 8 kilogram mass, times 4, 0, plus the 6g weight, multiplied by -3, 1. On the left, this gives us a nice round 20g. On the right, we have 6g and 10g. Now doing that calculation will probably help you understand that you're not really reducing your work. Like I said, all you're doing is reducing the number of equations you're writing. Now we can divide through by 20g on both of these and write x bar, y bar is equal to 3 over 10, 1 over 2. Written in coordinate form, I would put 0.3, 0.5 for the center of mass. Now I do understand if you want to say that's not really any better, I prefer the other method, 2 separate calculations, and if that's the case, that's absolutely fine. Write it whichever way you are happier with. The next example is slightly different, but mostly just in the way it is shown. So we have a light rectangular plate. Let me highlight this here. This is a key word. You should know this from M1. A quick reminder, light means its mass is 0, which of course is unrealistic in the real world, but we're modeling here. So we have a light rectangular plate, ABCD, and the lengths are AB is 10 centimeters, AD is 20 centimeters. Particles of masses 1, 2, 3, and 4 kilograms are attached to the plate at points A, B, C, and D respectively. Find the distance of the center of mass from AD and from AB. Now this is a situation where I would draw a diagram, just to have A, B, C's, and D's all in the right places. So our rectangle, something like this. The shorter length, AB, is 10 centimeters. So A, B, C, D, like this. You would normally name your corners in order around the shape with the order given in the name. So if I start A, B, then convention says this should be C and this should be D, not the other way around. But you can also see in the question that B and D are either side of A. So here we've got 10 centimeters and 20 centimeters. And then we've got particles of masses attached to the corners. A is a 1 kilogram mass. B is a 2 kilogram mass. C is a 3 kilogram mass, that's 3g weight, and then a 4g weight at D. And the point of it saying that this is a light rectangular plate is not to confuse you. The plate itself has no mass. We're just looking at these masses on the corners. So it's not really any different to having an XY coordinate grid, which is actually the very next thing I'm going to draw on. I'm going to take one of these points as a 0 point. Just because it's in the bottom left, I'm going to take this point D as the 0 point and put on an XY coordinate grid. So this would be the X, and here the Y. And the whole point of this example is to show that sometimes you'll have to put that on yourself. You will have to decide where your origin point is, the point you're going to be measuring distances from. Putting it on one of the corners rather than, for example, down here somewhere, is really nice because it means that the distance for D, the 4g weight, is going to be 0 in both directions. We can also see now what it means when it says find the distance of the center of mass of the loaded plate from AD. From AD, what that means is find the distance in the x direction, because AD is effectively the y-axis. But from AB is different. Finding the distance from AB means we're going to have to find the y-coordinate first, let's say it's here or something, whatever this distance is, and then subtract that from 20 to find the distance from AB. So this is one reason why I would draw a diagram in this case, because it's not entirely clear what these are going to be. This is a coordinate that we normally do. This is not one of the coordinates that we normally find. And I hope it doesn't confuse anything if I quickly throw in here that it would have been a coordinate if I had drawn my diagram the other way around. A, B, C, D. Then AD would still be the y-axis and AB would have been the x-axis. But of course then the masses would be in different places and my calculation would have been different, such that the very final answer that we get would be the same. Okay, that's a lot of explanation. Let's get into the calculation. Our combined masses, 1, 2, 3, and 4, gives us 10g on the left, times by x bar, y bar. Now that has to equal 1g times 0.20 plus 2g times 10.20 plus 3g 10.0 and 4g times 0.0. I'll phrase the next line slightly differently. I'm going to put the 10g multiplier inside here, like this. And on the right hand side, same as before, 50g on the x and 40g on the y component. And then I'll say it like this. I'm going to equate the x components. So 10g x bar has to equal 50g. And 10g y bar has to equal 40g when I equate the y components. And that's not really any different to what we did last time, it's just a slightly different way of thinking about what's going on. And it still gives x bar, y bar to be 5 and 4 respectively. So it's halfway along this side, 5 centimeters, but it's only 4 centimeters up this side. Now I have to return to the question, because as we saw, this is not one of these numbers. AB is the distance from this side here. That is going to be 16 centimeters. And AD, the distance from this edge, that is 5 centimeters. So the answer to part A, the center of mass, is 5 centimeters from AD. And in part B, the center of mass is 16 centimeters from AB. Just be careful, you know exactly what it's asking you to find. Our next example has something different that is missing. Particles of masses these are placed at the points these, and you can see that one of these points is unknown. Given that the center of mass of the 4 particles is at the point this, so now we know the center of mass, find the values of x and y here. And don't panic, this is really very similar to what we've been doing already. The only difference is that our unknowns are going to be on the right hand side of the equation. So I form the same equation using the same formula in the same way. On the left we've got the total weight, 2 plus 2 plus 1 plus 5 is 10g, times the center of mass, which in this case we know, minus 0.1 and 1.1. Has to equal the combined moments of the individual masses. So we've got 2g times the thing that we don't know, xy, plus another 2g times 40, plus g times 4 minus 3, plus 5g times minus 3, 2. And then we just rearrange as necessary to find x and y. On the left we've got minus g and 11g. On the right, 2gx, 2gy for the first one, and then I'll add the other 3 together, which gives me minus 3g in the x component and 7g in the y component. And then you solve this depending on how you want to do it. You could add these together and then equate that line with minus g and this with 11g, or you could do what I'm going to do, combine these two vectors and do it this way. So we've got minus g. If I take that over there, that's minus 3g. So we've got 2g and 4g is 2gx and 2gy. And from there we've got a 1 and a 2 for x and y. So x is equal to 1 and y is equal to 2. Our final example is kind of like this, same equation, but a slightly different thing we don't know. 3 particles of masses 2, 5, and m are placed at the points this, this, and this respectively. Given that the centre of mass of the 3 particles is at the point this, find the values of m and x bar. So we've got some information. We've got the masses here, we've got all of the points here, and we've got y bar. So I can use the y coordinate to work backwards with what I know the answer is for the y bar to find m. Once I've found m, then I can work forwards again with all of that information to find x bar. So the problem solving element here is to realize that you have to find m first. And this might be a situation where using the vectors isn't going to be quite as helpful, because I'm going to use y bar first and then come back to x bar later. I've just realized that for all of the other examples I've been using weight with the g's involved, and actually the formula just says masses because every time we do it the g's always cancel out. So in this example I'll follow the formula and use the masses rather than the weights. So we've got 2 plus 5 plus m times y bar, which is 3, has to equal the individual y moments. And that's why I've been using weight, because I'm still thinking of them as moments. So we've got the 2 mass times by the y coordinate, 6, plus 5 times its y coordinate of 1, plus m times its y coordinate of 4. On the left, 21 plus 3m. On the right, 17 plus 4m. That gives us m is equal to 4. Now we can use that in our x bar equation and do pretty much the same thing, but now we've got m is 4 here, and x bar is the thing we want here. Using all of the x coordinates this time, 11x bar is equal to 12, so the x coordinate of the centre of mass is 12 over 11. And I hope those examples have been varied enough for you to have a go at the questions in exercise 3b. And maybe I'll see you for some laminas in the next video.